Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss related rates. For instance, we know that the volume of a sphere is equal to 4/3 pi r cubed, where r is the radius of the sphere. Suppose the volume is increasing at a certain rate. That means we know dv dt, where v is the volume. The question might be, does that enable us to figure out dr dt? Well, these kind of problems are called problems of related rates, and we want to discuss the general strategy for working them out. They all involve geometry. Related rates problem strategy. 1. Draw a picture and name the variables and constants. Use t for time. Assume that all variables are differentiable functions of t. 2. Write down the numerical information in terms of the symbols you have chosen. 3. Write down what you are asked to find, usually a rate expressed as a derivative. 4. Write an equation that relates the variables. You may have to combine two or more equations to get a single equation that relates the variable whose rate you want to the variables whose rates you know. 5. Differentiate with respect to t, then express the rate you want in terms of the rate and variables whose values you know. 6. Evaluate. Use known values to find the unknown rate. Well, suppose we have a cylinder. We can compute its volume in terms of the radius of the base and the height, and we have a simple formula. And now the question is, how does the rate of change of the volume relate to, for instance, the rate of change of the height or the rate of change of the radius, or both? Well, let's look at more details here. Volume. The radius r and height h of a right circular cylinder are related to the cylinder's volume v by the formula v equal pi r square h. So A, how is dv dt related to dh dt if r is constant? B, how is dv dt related to dr dt if h is constant? And C, how is dv dt related to dr dt and dh dt if neither r nor h is constant? Okay, so let's start with A, and we'll assume r is constant. We want to see how is dv dt related to dh dt. And I've used that wiggle symbol as sort of a generic symbol for the word related. So basically, we know v equals pi r square h, and r is constant. So when we look at this formula now, we're thinking of the pi r squared as simply a constant. And notice that would be the area of the base of the cylinder. So here's a picture of our cylinder, and here's the height, and the radius of the base is r. Then it's easy to see that the volume should be the area of the base times the height, which is then pi r squared h. So if the pi r squared is a constant, then when I differentiate the equation on both sides with respect to t, I'll simply get pi r squared times dh dt. What we can see here, for instance, is that the rate of increase of volume is simply the area of the base times the rate of increase of the height. That's an interesting geometric way to look at it. That is, for instance, if we think of only the height as changing, in a sense, if I fix the plane of the base here, what would happen as the height, for instance, increases? That would mean this top of the cylinder is growing upwards. And so what that's telling us is that the rate of increase of the volume is the area of this moving surface times the rate at which it moves up. Now let's take a look at part B. So in part B, we're interested in the rate of change of volume with respect to time in relation to dr dt, the rate of change of the radius, if we hold the height constant. Remember, our formula v equal pi r square h gives us the volume of the cylinder whose radius is r and height is h. So this time we want to keep the h constant and the r is increasing. So here we have this cylindrical surface for the walls of the cylinder, and notice as r increases, that grows in an outward direction. In effect, the surface is growing out normal to the cylindrical walls. H is constant, pi is constant, so let me write this for emphasis with the constants in front. We could say pi h r squared. And so in this case, since the pi h is constant, now dv dt is equal to pi h times the derivative of r squared, but with respect to t. Remember, we're differentiating with respect to time, and so in effect we have to use the chain rule because r is a function of time. We don't know exactly what it is, but that's immaterial. We have 2r dr dt according to the chain rule. Well, let's look at this for a minute. We have 2 pi r. I'm going to gather the 2, the pi, and the r together, the h and the dr dt. And so look what's happening now. 2 pi r is the circumference of the cylinder. And so when I take the circumference and multiply by the height, what I get is the surface area of the cylindrical wall, the vertical cylindrical wall. And so what this is telling me again is that the rate of increase of the volume is the rate at which this cylindrical wall is moving out in this normal direction multiplied by the area of the cylindrical wall. In effect, we're getting the same form for the rate of change of volume. In effect, it's the area of the moving surface which moves as the variable changes, multiplied by the rate that that variable changes. Well, let's look at part C now. This time, we're not going to allow anything to be constant, so we're going to look at our equation V equals pi r square h for the volume of our right circular cylinder. And now let's think of the base of that cylinder as sitting on a fixed plane. It has a radius r and a height h, and we're going to allow both r and h to change, and just to be definite for our thinking, we'll think of them as increasing, but in reality they could be increasing or decreasing. We don't know how they're changing. But in this case, we differentiate with respect to time both sides of the equation, and both of those variables, r and h, are now functions of time. So we have to use the product rule. The derivative of the first factor, r squared, is 2r dr dt multiplied by the second factor h plus r squared times the derivative of the second factor dh dt. Well, let's put these two together. That is, I'm going to multiply through the pi, and look what I'll have in the first term. 2 pi r, that's the circumference of the cylinder, multiplied by h times dr dt. And what's the second term? Pi r squared times dh dt. Well, remember, when we looked at how the volume changed when we held r constant, we got the area of the top multiplied by the rate that the top moves up. That's dh dt. That's this second term. And what's this first term? That was the answer to part B. That's the rate at which the volume is increasing due to the lateral, the vertical surface here, moving outwards in all directions normal to itself due to increasing r. It's a very interesting way to look at it. The rate at which the volume of the cylinder increases is simply the sum of the rates of increases due to the top moving up and the vertical sides moving out. Well, in many problems of related rates, we have to deal with the Euclidean distance formula in terms of rectangular coordinates. So it's interesting to see how the distance between 2 points varies as the coordinates change. Let's look at this in a little more detail. Distance. Let x and y be differentiable functions of t, and let s equal the square root of x squared plus y squared be the distance between the points x comma 0 and 0 comma y in the xy plane. A, how is ds dt related to dx dt if y is constant? B, how is ds dt related to dx dt and dy dt if neither x nor y is constant? C, how is dx dt related to dy dt if s is constant? Okay, so let's look at this. Part A then is how is ds dt related to dx dt with y as constant? And remember, our equation for s in terms of x and y is s equals the square root of x squared plus y squared. Now, in equations involving related rates, we can do rearrangements of the equations to simplify things where possible. And here what I'm going to do is square both sides to get rid of the radical. This equation is saying the same thing as s squared equals x squared plus y squared. So now, in this equation, I'm thinking of y as constant and x is depending on time, s is depending on time. These are unspecified functions of time, but we can differentiate both sides of the equation using the chain rule. The derivative of the left side is simply 2s ds dt equals the derivative of the x squared with respect to t is 2x dx dt. And of course, since the y is constant, so is y squared. And notice we get a very simple equation. We can cancel the 2's and solve for ds dt. This is a typical way these related rates problems goes. You differentiate an equation on both sides with respect to t and simply express the rate of change you want in terms of the rest of the information. So to get the ds dt isolated here, I just divide both sides by s. So this would be x over s dx dt. Now if you wanted this result totally in terms of x and y, I could replace s in this expression by its expression in terms of x and y. S is the square root of x squared plus y squared, and so we could also say ds dt is equal to x divided by the square root of x squared plus y squared multiplied by dx dt. Now let's look at part B. In this case, we want to see how is ds dt related to dx dt, both dx dt and dy dt in general. So looking at our equation s squared equals x squared plus y squared, we now just differentiate both sides with respect to t. Now s is some unspecified function of t, likewise x is, likewise y is now an unspecified function of t. So we're differentiating and applying the chain rule to every term. The derivative of s squared is 2s times its derivative with respect to t, ds dt, equals 2x dx dt plus 2y dy dt. Of course, we can cancel the 2's since they occur in every term, and now I can get ds dt isolated by simply dividing through by s. So ds dt is equal to x over s dx dt plus y over s dy dt. And of course, again, if you wanted everything in terms of x and y, you could replace s everywhere by its expression in terms of x and y. Remember, s is just the square root of x squared plus y squared. Well, what about in the case where we look for the relation of dx dt to dy dt when we keep s itself constant? So now we have the equation s squared equal x squared plus y squared. but now this s is constant, so consequently the s squared is also a constant. In this case, what we get is, on differentiating the left side, simply 0, because the derivative of a constant is 0. So 0 equals 2x dx dt plus 2y dy dt. Canceling 2's, we can solve this for dx dt. We would move the terms not involving dx dt to the other side of our equation, and so we get x dx dt equals the negative of y dy dt. And so finally just divide both sides of the equation by x, and we find dx dt is equal to the negative of y over x multiplied by dy dt. Well, let's look at an application of our relation between related rates and distance. In this case, we're going to deal with the classic problem of the sliding ladder. A ladder leaning against the wall, and it starts to slide from the base. Let's look at this in more detail. A sliding ladder. A 13-foot ladder is leaning against a house when its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at the rate of 5 feet a second. Okay, now the first step in dealing with a problem like this is to picture in your mind and draw a crude sketch. So that's what I'm going to do. You've got a wall, so I'll draw a vertical line representing the wall, and of course the ground, a horizontal line, and the ladder leaning against the wall. The base is moving at the rate of 5 feet a second away from the wall. So let's label that with a little arrow indicating the movement of the base. Now what we want to do is label the particulars of this picture with symbols. For instance, let's think of this intersection of the vertical and horizontal lines here as the origin of a coordinate system, and so we can make this the x-axis. The vertical line is the y-axis, and so we can make this distance be x, and of course x is changing in time because the base is moving to the right. The vertical distance will be y, for the distance from the ground to the top of the ladder. And so since the ladder has a fixed length, and I'll use the symbol S for the length of the ladder, which is 13 feet, constant, as the ladder slides, the base moves out to the right, and that's going to force the top to go down. So in our equations, we're going to expect that if we compute dy dt in this situation, it should come out to be a negative number, for instance. What other variables do we have here? Well, notice we could consider the angle theta that the ladder makes from the horizontal there. And what else? Well, this triangle formed by the ladder, the wall, and the ground has an area. The area of that triangle is simply 1/2 base times the height. How does the angle theta relate to y and x? Well, notice we've got a right triangle here, and so y over x is the tangent of the angle theta. So we can say tangent of theta equals y divided by x. So those are just some basic things we could immediately write down just from the physical setup of our picture before we're even asked anything. So that's our basic things. Now let's look to see what we're asked in this problem. A, how fast is the top of the ladder sliding down the wall then? So remember, the base is moving 5 feet to the right, so now we can compute how fast the top is moving down. B, at what rate is the area of the triangle formed by the ladder, wall, and ground changing then? And part C, at what rate is the angle theta between the ladder and the ground changing then? Okay, so let's begin. Here's a nicer picture of our situation, and I want to emphasize, in the case where you're working problems from the book, sometimes nice pictures are provided, but you want to be able to develop the technique of crudely sketching your own picture. And this is a certainly nicer picture of our situation. We have a nice picture of the 13-foot ladder. Here, for emphasis, x parenthesis t is indicating that the base position of the ladder is a function of time, and likewise, y parenthesis t is indicating that the top of the ladder's position y on the y-axis is a function of time. And here our down arrow is indicating, we've reminded ourselves that the top of the ladder will go down as the base of the ladder moves to the right. Well, now that we've set up our problem and seen the geometrical relationships, let's start working out the various parts. Okay, so the first thing we have to do is figure out dy dt, the rate at which the top of the ladder is sliding down the wall. Remember, here's our crude little picture. The ladder is 13 feet long. X is the distance of the base from the wall. So notice what we have here is a right triangle, and S, which is 13 feet, is the length of the ladder. We have this right triangle, and the ladder is forming the hypotenuse. So naturally, S squared is x squared plus y squared, and that's our basic formula. So what we would do is differentiate both sides of this equation, and that'll give us our relationship. Notice, since S is constant, the derivative of the left side is 0. So we get 0 is 2x dx dt plus 2y dy dt. 2's cancel, and dy dt is simply the negative of x over y dx dt. Such a simple equation to solve. And so consequently, what we're interested in is what dy dt is exactly, and what we know is that dx dt is 5. It's moving to the right, so x is increasing, and therefore that's a plus 5. We're interested in what is dy dt when x equals 12 feet. Well, notice we also have to know y, and y hasn't been given to us. But remember, this original equation that we differentiated has on the left s, which is 13, we know that, x, which is 12, we know that, and so consequently we can solve it for y. We see that y is simply the square root of 13 square minus 12 square. Well, 13 squared is 169, 12 squared is 144, and so that's the square root of 25, which is simply 5. In other words, at the instant we're interested in, y is actually just 5 feet. And so that tells us that dy dt is simply the negative of 12 fifths dx dt. Well, notice y and dx dt are exactly the same, aren't they? So in effect, this cancels that, and dy dt is the negative of x, just for these particular numbers. So dy dt is negative 12. So let me put this over here, negative 12 for dy dt. What's the significance of the negative sign? Remember, we said that it's clear from the picture that the top of the ladder has to go down, and consequently that means y is decreasing, and so we expect to get a negative rate of change for y. And so that negative 12 is telling us that the top of the ladder is moving down at 12 feet per second. Now let's look at part B. In part B, we want to figure out the rate at which the area is changing. That's the area of the triangle formed by the base distance from the wall to the foot of the ladder, and that which we're calling x, and the top of the ladder, and the ladder is hypotenuse of that little right triangle. So we know that area is 1/2 x times y. We want to find dA dt. That's the question. Here again, x equals 12 at the instant we're interested in, and at that instant the base is moving to the right at 5 feet a second. And we've just figured out in part A that at that instant y equals 5. And so now we take this equation for A in terms of x and y, differentiate both sides with respect to t. So we get 1/2 times, and now we use the product rule. Remember, x and y are both functions of t, so derivative of x with respect to t multiplied by y plus x times the derivative of y with respect to t. And so now we just put in what we know. Remember, we just figured out that dy dt is -12 from the previous part. And so we now know everything in the right side of the equation. dA dt is 1/2, dx dt is given to us as 5, the y is 5, plus the x is 12, the dy dt is -12, and so we get 25 minus 144 divided by 2. So 25 minus 144 over 2, that would be -119 over 2, which is -59.5, and we're dealing with area here, and so that would be square feet or feet square per second. And so there's our rate of change of area here, the final answer. Notice the negative sign there means that as this ladder is moving to the right, when x is 12, the area of this triangle is actually decreasing. Now let's look at the last part of our problem. We want to find the rate of change of the angle that the ladder makes with the ground. So here in our little sketch, here's the ladder leaning against the wall. Its length is s equal 13 feet. The vertical distance of the top of the ladder from the ground is y, and the horizontal distance of the base of the ladder from the base of the wall is x. The base of the ladder is moving to the right at 5 feet a second, and we're interested in d theta dt when x equals 12 and y equals 5 feet. Okay, so remember, dx dt is 5 feet, and we've already figured out that dy dt is -12 feet per second. That's dx dt is 5 feet a second, dy dt is -12 feet a second. So we look at our picture here, and remember, tangent of theta is y over x. So we can write the equation tan theta equals y over x. And of course, our technique for getting d theta dt is just to differentiate both sides of the equation with respect to t. When we do that, we'd be involved with the quotient rule, and so we can simplify this by instead multiplying the x out first. We get x times tangent of theta equals y. So now let's differentiate this equation on both sides with respect to t. So in the first expression on the left, we have a product of two functions of t, so we have to use the product rule. The derivative of the first factor then is dx dt multiplied by the second factor tangent of theta plus x, and now we have to multiply by the derivative of tangent of theta with respect to t. So the derivative of tangent is secant squared, so we get secant squared of theta, but then the chain rule tells us we have to multiply by d theta dt. And that all equals the derivative of the right side, which is simply dy dt. Now at this point, we know everything in this equation except for the d theta dt. So for instance, dx dt is 5. The tangent of theta, remember, is y over x. Y is 5 and x is 12, so that's 5 divided by 12 plus x, which is 12. Secant of theta, remember, is s over x, so that's 13/12. So we want the secant squared, 13 squared over 12 squared times d theta dt equals, and now dy dt, what's that? The -12. You see, everything in our equation is now just numbers except for the d theta dt, and so we can easily solve that one for d theta dt. Let's simplify this a little bit. I'm just going to slide this up a little bit, and when we do, we can see, notice in this equation I can multiply through both sides by 12, and it'll get rid of a 12 here. And notice it gets rid of one of the factors of 12 here, and the other one will cancel with this 12. So we'll end up with 5 squared plus 13 squared times d theta dt equals the result of multiplying the right side by 12, which is negative 12 squared. So now let's move this 5 squared to the other side. We have 13 squared d theta dt equals negative 12 squared minus 5 squared. Well, remember that's 144 and 25 is 169, which is 13 squared. So we're ending up with negative 13 squared over here on the right side of our equation. And so now we see they easily cancel, leaving simply d theta dt is negative 1. Well, what does that negative 1 mean? First off, what are our units? Remember, when you're dealing in problems like this using geometry, the angles are in natural units, which are radians. So consequently, since our time is in seconds, the units here would be radians per second. So the angle is changing at the rate of negative 1 radians per second. Coming back to our picture here, you see I've drawn the angle as measured in the positive direction in this direction, and so consequently a negative d theta dt means the actual motion of the ladder is down that way. The angle theta is decreasing at that instant at the rate of 1 radian per second. Now let's work an applied problem where we're dealing with distance and everything's in motion. A balloon and a bicycle. A balloon is rising vertically above a level, straight road at a constant rate of 1 foot per second. Balloon is going up. Just when the balloon is 65 feet above the ground, a bicycle moving at a constant rate of 17 feet per second passes under it. How fast is the distance s of t between the bicycle and the balloon increasing 3 seconds later? Okay, so let's draw a crude picture of this situation. Our balloon is going up 1 foot per second. And at the instant that we're interested in, one of the instants we're interested in, a bicycle goes by. There's a crude picture of a bicycle with a little person on the bicycle. There's got handlebars maybe. Doesn't have to be a very good picture. At that instant, the distance here is 65 feet. Now, the bicycle is moving to the right at 17 feet per second. So what's the situation in general? This is a very specific snapshot. In general, what we've got is the balloon is going up, the bicycle's somewhere over here, and here's the little guy on the bicycle, and it's moving to the right, and we're interested in this distance of separation, which is s as a function of t. What we want to know is, what is the rate of change of s of t? How fast is that distance increasing? And at the specific instant we're interested in, 3 seconds has elapsed from the time the bicycle was directly under the balloon. So here we have a vertical line down to the ground formed by a straight line from the balloon down to the ground. And then we have the horizontal line, which is the ground. And the distance from this point directly under the balloon to the bicycle, let's call that x. The distance from the ground to the balloon, we'll call that y. And of course, the distance from the balloon to the bike has been specified for us as s of t. Now, at the instant we're interested in, that's 3 seconds after the bike was directly under the balloon. So how far could the bike have gone? Well, it's going 17 feet a second, so in 3 seconds, it goes 3 times 17 feet. And so we're interested at the instant x equals 3 times 17, which is 51 feet. Now, how about the balloon? Where is the balloon at this instant we're interested in? Remember, at the start of our situation, the bike is directly under the balloon, and the balloon is 65 feet high. The balloon is moving up at 1 foot a second, so in 3 seconds it goes up 3 more feet. And so at the instant we're interested in, y is going to be 68. I'm going to write this here. Y equals 68 feet at the instant we're interested in. So notice I have now the value of x at the instant we're interested in, the value of y at the instant we're interested in. And so how would I figure out the value of s at the instant we're interested in? Well, notice there's a right triangle. And what's the relation between s and x and y? Always. Well, obviously what we have is s squared equals x squared plus y squared. And so that means because I know x and y, I can easily figure out s. Well, now let's look at a nicer picture of our situation since we have one. And remember, when you're working these problems, you don't need to have a picture that's this nice. But the essential thing here is you draw a crude sketch, and when you draw your sketch, I'm sure you can easily picture something like this in your mind. And so the essentials are s squared equals x squared plus y squared. S, x, and y are all changing with time, and so let's differentiate both sides with respect to time, keeping in mind that all our variables are functions of time, so we're using the chain rule. Derivative of s squared is 2s ds dt. Derivative of x squared is 2x dx dt. Derivative of y squared is 2y dy dt. And notice we know all the rates of change on the right because dx dt is the rate that the bicycle moves to the right. Dy dt is the rate that the balloon is moving up. So we know dx dt was 17, dy dt is 1. We know what x is, we know what y is. We can cancel the 2's. Okay, so then we have ds dt equals x over s dx dt plus y over s dy dt. And so all I have to do is use the equation s squared equals x squared plus y squared to find s, and then I've got the entire right side. So we'll do that next. Okay, so again, here's our equation for ds dt. On the right, you see I need to know x, s, dx dt, y, s, dy dt. And of course, I know x and y already. Remember, x was 51. Actually, it was 3 times 17. Y is 68. And of course, it's going to be useful here just for simple calculations to notice that 68 is 4 times 17. So 4 times 7 is 28, carry 2, and you get 68, you see. And so notice now with these factorizations, it makes it quick to find s squared. S squared is 3 squared times 17 squared, which is x squared, plus 4 squared times 17 squared, which is y squared. And so now factor out the 17 squared. We have 3 squared plus 4 squared times 17 squared. And 3 squared is 9, 4 squared is 16, so we get 25 times 17 squared for s squared. And so s is the square root of 25, which is 5, times the square root of 17 squared, which is 17. And so there we have s is 5 times 17. And of course, 5 times 17, let's see, 5 times 7 is 35, carry 3, we have 85. So at the instant we're interested in, s is 85 feet. And so what does that give us for ds dt? ds dt is then x, which is 51 over 85 times dx dt. Well, remember dx dt is the velocity of the bicycle, which is 17, plus y, which is 68, divided by 85, times dy dt, which is just 1. And of course, actually, remember the 51 is 3 times 17, the 85 is 5 times 17, so that one is 3/5. The 68 is 4 times 17, the 85 is 5 times 17, so this is 4/5. And so we have 3 times 17 plus 4. 3 times 17 is 51, and 4 is 55, so we have 55/5, which is simply 11. So that means ds dt finally is just 11 feet per second. And there we have it. Now let's work a related rates problem involving volume. When surfaces change and regions inside them change their volume, it's a general principle you'll notice that the rate of change of volume is equal to the surface area of the surface that moves out multiplied by the rate at which it moves. The next problem we're going to see illustrates this. The radius of an inflating balloon. A spherical balloon is inflated with helium at the rate of 100 pi cubic feet per minute. How fast is the balloon's radius increasing at the instant the radius is 5 feet? How fast is the surface area increasing? Well, let's draw a crude picture. So our balloon is spherical, so we draw a picture of a little sphere here. And its radius, we'll call it r. We have to give all the various variable symbols. Now the r is not constant, it's changing because as the balloon inflates, the radius grows. Now what we know about the relationship between the volume of a sphere enclosed by a sphere to the radius is the volume V is 4/3 pi r cubed. And so when we differentiate both sides of this equation with respect to t, we'll find dv dt is equal to 4/3 pi times 3r squared dr dt, according to the chain rule. Remember, the derivative of r cubed is 3r squared with respect to r, but we're differentiating with respect to t, so we have to multiply that by the derivative of r with respect to t. R is some function of t, and we don't know what it is. However, notice the 3's cancel, and so what we're left with is dv dt is 4 pi r squared dr dt. Are you familiar with the significance of 4 pi r squared in relation to a sphere? Well, that's the surface area of a sphere of radius r. We'll call that capital S. So in effect, dv dt here is simply S times dr dt. In other words, we have a very simple relationship between the rate of change of volume, the surface area, and the rate of change of radius. Well, notice as the radius increases, the rate that the radius increases is effectively the rate at which the surface of the sphere is moving out in all directions, perpendicular to itself. Sort of everything is moving out in what we would call the normal direction to the sphere, and the rate at which that spherical surface is moving out due to the balloon inflating is dr dt. And so our rate of change of volume is simply the area of the moving surface times the rate at which it moves out. So now we can easily calculate from our information what the various quantities are. For instance, what do we know? We know dV dt because we're given the rate that helium is increasing the volume of the balloon. That's 100 pi cubic feet per minute. We're also given the radius of the balloon at the instant we're interested. That's 5 feet. So let's write down our basic information then. We have dV dt equals S dr dt, with S equal 4 pi r square. The instant we're interested in, r is 5 feet, and we know dV dt is 100 pi cubic feet per minute. So what about S at the instant we're interested in? S is 4 times pi times 5 squared. 5 squared is 25 times 4 is 100 pi. So at the instant we're interested in, S is 100 pi, and of course our units of length are feet, so this would be square feet. So let's look at our equation here. dV dt is S times dr dt. dV dt numerically is 100 pi. S numerically is 100 pi, so that equation becomes 100 pi equals 100 pi dr dt. And so that tells us dr dt is simply 1 foot per minute. What about ds dt? Well, ds dt, we come back to our equation for S in terms of r. That's 4 pi r squared. We differentiate that with respect to t, so we get 4 pi 2r dr dt. And so at the instant we're interested in now, remember r is 5. 2 times 5 is 10, times 4 is 40. And so we get 40 pi, dr dt is just 1. So we have 40 pi feet per minute. Well, let's think of our units here carefully. What do we got? There's an r, there's an r, so we've got actually r square, feet square per minute. We're dealing with the rate of change of surface area, so our units had better be square feet per minute in this case. So to summarize the final answer then, we have dr dt is 1 foot per minute, and ds dt is simply 40 pi square feet per minute. Okay, now that you've seen some of these problems on related rates work, you might want to try some on your own.